AP Physics, this is Unit 4, going to be from the student workbook 4.h, potential energy and choice of zero. The scenario goes as follows. An ideal spring of an unstretched length of L naught equals 0.25 meters, and spring constant K equals 50 newtons per meter is hung vertically above a level floor as shown in the figure A. A 1.0 kilogram block is attached to the spring when it is at its natural length, released and allowed to move freely. So we got a couple of distances that we've got to worry about here. The first one is that the total height from the ground is 1.0 meters. We also know that the unstretched length is going to be 0.25 meters, and we're going to take this and we're going to drop it, and it looks like it drops to an equilibrium position right here. Let's see, part A, it says draw and label the forces exerted on the block in the diagram. Qualitatively consider relative magnitudes of the forces. So in other words, you don't have like solid numbers just quite yet, but go ahead and just qualitatively, so you don't have to specifically list out the arrow links numerically. The equilibrium point of the block spring system is shown as a dotted line. So that means that the equilibrium position is a place where you're going to be moving back and forth and back and forth. So if we were to let this spring just kind of play out, what it would do is it would oscillate back and forth around this equilibrium position. And what we're looking for is the forces like at that equal point whenever it's in between the up and the down motion. So let's think about the forces on the first part where it's just 1 kilogram and it just at the very beginning just gets dropped. Well, at the very beginning, whenever it gets dropped, the spring is unstretched at this point. It's just in a natural position. So we're going to say that the only force acting on this 1 kilogram mass is going to be mg. That's the only force that's actually pointing downward. On the other side, gravity doesn't change, so even though it's passing through its equilibrium position, there's still going to be a force down, and try to make sure that it's the same arrow length relatively as the one before it. You don't want to put a really short gravity arrow on the right side and a really long gravity arrow on the left, because the AP graders will start to think that you are have different values for gravity, and you don't want that. However, in this place, there's also a force of the spring that's also pushing up here, because now once you've actually started to pull this down, the spring is actually being stretched. So we're going to have Fs that kind of points upwards. Okay, so we got two forces here, mg and Fs. We know that the force of the spring is going to be less than the force of mg because this object is still going to be moving downward. Oh wait, hang on, I may be lying to you. I am lying to you. Hang on. Let's see here. Haha, just kidding. When you're at your equilibrium position, you're neither speeding up nor slowing down. So you're going at a constant speed just at this equilibrium position. The forces are going to change as you go along through it, but the only thing it's really asking for is the equilibrium position itself. So we should make this gravity force mg that's pointing downward the same arrow length as the force of the spring that's pushing upwards. So therefore, you're going to have balanced forces specifically at that location. Okay, at any other point in the spring, those forces are not going to be balanced to each other, and you're going to have acceleration that pulls it either up or down as it oscillates back and forth, as it goes through that simple harmonic motion. So let's see here. We got the equilibrium point. I think that's it for part A. There's no other forces acting on it. Nothing's pushing it to the left or to the right. So let's see here. Part B, calculate how much of the spring has stretched when the block is at equilibrium. So like we mentioned previously, when it's at equilibrium, that's the case on the right side, you've got an equal amount of forces. There's an upward force of the force of the spring, and there's a downward force of the force of gravity. So you've got Fs pulling up, and you've got mg pulling down. So that's going to balance the forces out. So let's just kind of think about this in terms of a Newton's second law problem. So we've got the net force that's acting on the object is going to be equal to both of these forces put together, and both of those forces put together is going to equal 0. So let's write these out. That's going to be the net force is going to be, let's consider upward positive. So it's going to be the force of the spring minus mg, and that's going to equal 0. Well, that means that we can set both of them equal to each other and just move it over to the other side. So I'm going to add mg to both sides. So the force of my spring, which is by Hooke's law, kx, that's going to be equal to mass times acceleration due to gravity. You get kx is equal to mg. Let's see here. We know what the mass of the object is. So we know this. We know what acceleration due to gravity is, so we know this. And we know the spring constant, so we know this. We should solve this for x, and we should see what we get. So that's going to say, let's just divide both sides by k. So it's going to be x is equal to mg over the spring constant k. And we have all of those values, so let's go ahead and put them in. The mass is 1 kilogram. The acceleration due to gravity, let's just use 10 meters per second squared. And the spring constant K is 50 newtons per meter. Here we go. And let's run this through and see what we get. So 1 times 10 divided by 50. And let's also make sure that we look at the units as well too. Let's see here. A kilogram meter per second squared is a newton. So we're going to get some cancellation that occurs. There's going to be cancellation here. For the kilogram meters per second squared, and the newtons are going to cancel. That leaves you with a meters on the denominator in the bottom, which means you can flip it back up to the top. So your answer is going to be in meters. That's a good thing. That means this equation makes physical sense. So if we do 1 times 10 divided by 50, that's going to give you 0.2 meters for our stretch distance. So that means this distance from here to, see if I can get it going here. From this location in green down is going to be 0.2 meters. Okay, so that is part 1 for part B. And then the next one says calculate the height of the equilibrium position of the spring with respect from the floor. Okay, I don't think that's necessarily too bad because we're just looking for the equilibrium position, which is right here along that dotted line. So the only thing we have to do is we just have to take our 1 meter that we have and subtract out the distances that are given to us and that we figured out. So it's going to be 1 meter for the total distance up to the top. We're going to take away that 0.25 meters, and then we're also going to take away the equilibrium distance, which is 0.2 meters. And whenever you subtract all of those together, that's going to come out to be 0. Let's check it out. 0.55 meters. And that's going to be where your equilibrium position is. All right, so now let's get into the energy part. For part C, it says that Angela is tasked with completing energy bar charts for the scenario described above and creates the chart below and left for the time just as the block is released. Complete the energy bar chart below and right that you would, below and right, okay, that's like the bar chart that's below and to the right. That you would depict the energy of the block Earth spring system as the block passes through equilibrium. So it's looking for what the energy chart is going to look like right at the equilibrium position. So we're going to have to look and see how much energy we gained and how much energy we lost in this system. So let's see what we can do about this. So on the left, it says that Angela came up with 7.5 joules of energy for gravitational potential energy. Before it was being released, she also said that there was 0 kinetic energy and 0 spring potential energy because the spring wasn't really stretched yet. So we know that on the right side, the gravitational potential energy is going to go down. We also know that the spring potential energy is going to go up, and we also know that the kinetic energy is also going to go up too because this object is going to be in motion. So in order to find out how far we actually need to make these, because they've got numbers here and the bar graph is important, you don't want to just add up random numbers. They need to add up to the same amount of energy on both sides according to the law of conservation of energy. So let's go ahead and do a quick spring potential energy calculation. So the spring potential energy would be equal to 1/2 kx squared. We have information for all of these values. It's going to be 1/2 the spring constant, which would be 50 newtons per meter, times 0.2 for the stretch position to the equilibrium position, meters squared. This should give you an answer in units of joules. So let's try to work these through. So it's going to be 1/2 times 50 times 0.2 squared, and that comes out to be 1 joule. Okay, so for the Cuggus part, I'm going to put 1 joule of spring potential energy right here. Now, we could try to come up with some formulas to describe out what the kinetic energy is, but we don't have to, because if we know what the spring potential energy is, then the rest of it has to be kinetic energy that got transferred over. So if we have, let's see, 1 joule of kinetic energy, or sorry, I'm sorry, not kinetic energy. If we have 1 joule of spring potential energy here, then that means that there's also going to be 1 joule of kinetic energy as well too. And we can figure that out using the kinetic energy is equal to 1/2 mv squared if you wanted to. You could also use the work energy theorem. So you could say that the change in kinetic energy is equal to, see, the change in kinetic energy is equal to the work done. That could be done as well, because you could find out how much work was done by changing the spring over from one location to the other. So let's go ahead and write that out. So there's going to be, let's see, 1 joule of kinetic energy right here. And if there's 1 joule of kinetic energy and 1 joule of spring potential energy, then we just have to take away that 7.5. So 7.5 minus 2 joules is going to come out to be 5.5 joules of gravitational potential energy. So I'm going to go ahead and just make this bar. Let's go ahead and fill it in. And that's going to be what the chart looks like whenever you're passing through the equilibrium position. Okay, and this is also using your reference point as from the ground. So if you were to use a reference point at a different position, you would get a different bar chart, but the end result would your interpretation would be the same. So I think that's actually the next part that it actually says. Oh, hey, look, it even says down at the bottom when UG equals 0 at the ground, just like Angela did. Okay, next part, it says Dominique says that the height above the ground doesn't matter, only the change in height is relevant. She considers the equilibrium position to be 0 gravitational potential energy. Complete the energy bar chart for the block Earth spring system when the block is initially released. Okay, so what we need to do there is, let's see here, the only thing that we would be considering is the gravitational potential energy that changed from the equilibrium position. So we know that from the equilibrium position there was a total change in position of 0.2 meters. So therefore we can deduce from this location that the total gravitational potential energy that you would have during that change would be equal to the mass times the gravity times the height. So we would say that our mass would be, well, it's 1 kilogram. The gravity would be 10 meters per second squared. And then the height that actually traveled would be 0.2 meters. So this one's a little bit of a mental math calculation. 10 times 0.2 comes out with 2 joules. And this is a really good way that you could actually make that argument up there for the top graph of that 1 joule of kinetic energy. It makes a little bit more sense down here whenever you're looking at just that delta x. So let's see, when it was just released, let's say that there were 2 joules of gravitational potential energy. And the same thing that was in the graph above should still be true. When it was just released, there was no kinetic energy acting on the system, and there was no spring potential energy acting either, because it was in its natural position. It wasn't in its equilibrium position. It was unstretched. So when it goes through its equilibrium position, it's already passed through that 0.2 meters. So that means that the gravitational potential energy went away. But if we ran the calculations again for that 1/2 kx squared, you would get exactly the same thing. So I don't think we need to write it again. I think we just need to kind of go up and scroll up and look at it. Whenever we calculated the gravitational potential energy right here, we found that it was just 1 joule, and the distance that was really important was this 0.2 meters. That didn't really change if you're looking at the equilibrium position. So we still got 1 joule of work being done. So that didn't change. There was 1 joule of spring potential energy. And then likewise, we could say, well, if there's 1 joule of spring potential energy, then the kinetic energy has to be what's left over if energy is conserved. So we can then, by deduction, go ahead and fill in that 1 joule of energy on the other side as well too. So you notice that on the graph on the bottom right that you have 1 joule of kinetic energy and 1 joule of spring potential energy, and that energy got traded over from gravitational potential energy. And then if you look at the top one, you have 1 joule of kinetic energy and you have 1 joule of spring potential energy, and both that 1 joule of spring potential energy and kinetic energy got traded over from gravitational potential energy. So the end result is actually the same in both cases. So I think on the next part it says, use the results of your bar charts to support Dominique's claim that the 0 point of the gravitational potential energy does not affect the behavior of the block Earth spring system. Reference specific details of the student's energy bar charts in your answer. Okay, so what you want to look for is you want to pay attention to what happened. And remember, I want you to put this in your own words. So pay attention to what happened with the kinetic energy and the spring potential energy in both of them. Pay attention to that. Okay, and also pay attention to the conservation of energy, if I can spell it. Because if you look at it, you should see that you have the same amount of energy on both sides. So try to reference the kinetic energy and the spring potential energy on the right side and describe what's happening there. See how there's not really a change in between both of those. And that should pretty much get us through it. I think that's the last part. It certainly is. So you guys have a great day, and I will talk to you later.